Welcome to our first chapter, Chemistry Chapter 1, Essential Ideas. This is the in-class video lecture, and we will be discussing today the first three sections, Chemistry and Context, which is a section really that just introduces us to the idea of chemistry and the things that we'll be studying. And in Section 2, we'll look at the phases and classification of matter. What is the composition of matter, such as pure, mixture, element, compound, and how do we classify things as solids, liquids, and gases? And in our third section, we'll talk about chemical and physical properties and chemical and physical changes, the first three sections of our first chapter. Taking a look at our first visual, I wanted us to just take a moment, kind of process, and if you have a neighbor nearby, you can engage in a conversation. And if you're at home listening to the lesson through Canvas, take a quick peek with me at the very center of our graphic, the word chemistry. And we'll notice that chemistry is termed the central science. My question for you is, why are we studying chemistry? What is this thing we call chemistry, and how does it relate to your particular career pathway? Just take a moment to yourself and decide how your pathway leads back to that central science known as chemistry. We can see a variety of things in the life sciences, such as medicine, toxicology, biology, food science, all tying back down to biochem, leading to chemistry. Perhaps you're a math or computer science major and can tie back to the computations studied in chemistry. All kinds of a variety here, and we're just taking a moment to discuss how your career pathway leads to the science of chemistry. We mentioned that chemistry is indeed called the central science. Its textbook or classic definition, it's the study of composition, properties, and the interactions of matter. I say it is the study of matter and the changes it undergoes. We'll write that down together. The study of matter and the changes it undergoes. That's what's interesting to a chemist, is how we can take one form of matter and changing into something that's more helpful to our society. So as we proceed through our course, you're going to discover many different examples of changes in the composition and the structure of matter. How we classify these changes, are they chemical or physical, and how they occurred. We'll start recognizing causes, be able to predict energy changes that accompany these changes in composition, and the principles and law involved. So in our first section, we're going to take a quick peek at the scientific method. We'll differentiate among the terms hypotheses, theories, and laws, and will identify the dependent and independent variable when provided an experimental design. Our definition, it's an important one we should know. The scientific method, the path of discovery that leads from question and observation to a law, or perhaps a hypothesis that leads to a theory, combined with experimental verification of the hypotheses and any necessary modification of the theory. To me, I define the scientific method, really it's just a logical approach to solving a problem. Write that with me, a logical approach to solving a problem. What happens along the way is adjustment. So if we have a certain problem or a question, we start finding out how we can answer that question and modifying our ideas if our data collected suggests we need to. Let's take a moment and look at the slide that I'm about to present and talk to someone if you're in class nearby about the information, or if you're at home listening to the lesson, simply take a moment to reflect on this particular slide. I'm asking you, what is the scientific method? Staring at this visual, what information do you glean about this process? I notice that it's a flow chart, and the flow chart has arrows that point both up and down because it's a process that's ever changing. If I ask a question, I begin by researching that question. What have others figured out about it? I'll construct a best guess known as a hypothesis. I'll test my hypothesis with experiments and start collecting data to analyze and begin drawing conclusions. Is my hypothesis true? Have I proven it so? Maybe I'm ready to report results. But what if it's false? Which is just as valid as finding a truth. Finding an information that needs adjustment is also important. You think again, go back to the drawing board, and you go through the process as many times as it takes until you reach the results that you can report. These are important definitions I need us to know. The term hypothesis, that's your tentative explanation of observations. They act as a guide for gathering and checking that information. And it's what we test through experimentation, through calculations and comparisons from experimental results of neighbors, other scientists. Hypothesis, a tentative explanation. It's our best guess with the information we have thus far. These two terms we really need to be able to differentiate, to distinguish one from the other. They are the word law and theory. Laws, they are a summary of a vast number of experimental observations and describe or predict some facet of the natural world. Theories are well substantiated, comprehensible, testable explanations. So when I think of this in terms of how we can distinguish between these two terms, a theory tries to explain a particular aspect of nature. They're accepted because they provide satisfactory explanations with what the current knowledge is or the current technology. Let's give an example. We have something called the law of gravity. In physics, whenever I hold an object up high, that potential energy it possesses, if I release that object, it will fall to the ground. There is this force in the universe known as gravity. It does not explain why, it is just telling us it is. However, in the world of theory, we have the theory of the explanation of what an atom looks like, known as the atomic theory. It truly evolves over time as we learn more and more about the structure of an atom with our increasing technology. A theory is attempting to explain a particular aspect of nature, and a law will summarize a vast number of observations, and it's used to describe or predict something about the natural world. Here's yet another view of the scientific method. Let's take a moment and go through this flow chart, because really it's the same as the first flow chart I showed you for the scientific method, but presented in a little different format. I have an observation, something I'm curious about, so I begin to form a hypothesis and make predictions. From my predictions, I start performing experiments and making observations. Let's suppose it didn't answer my question, so I go back and reform my question, and I keep this loop going until I can contribute to the body of knowledge. If testing yields constant observations over a long period of time, we develop a law. If much additional testing supports the hypothesis, we may be able to form a theory, a tentative explanation. Let's see how you're doing with those particular words. Pause this video and try discussing in your own head if you're at home, or with your classmate if you're in class right now. Which one of these belong to the hypotheses, the theory, and the law? Number one, an untested explanation based upon observations or known facts. It's not yet tested is a key word. I'll call that one. I'll go down here for two. A botanist guesses, but it's not yet verified, that plants with one red flower and one white flower will have pink flowers. It's guesses. Let's call this one three. A description that predicts what happens, but does not explain how. It will predict, but without an explanation. Interesting. Let's call this 4. Scientists, after many experiments, state that matter is composed of atoms. Many experiments. An explanation that has been tested and verified, we'll call that number 5. I'd like you to pause this video and really try these to test your understanding of the vocabulary. And when you're ready, come back and we'll check your work. Well, welcome back. How did you do? There were 2 labeled as hypotheses. There were 2 labeled as theory, and only 1 labeled as a law. And I'm providing on the screen something you can pause and read through if you want further explanation of the why we placed each clue in the column we did. Keep practicing if you made some mistakes. Here's another sapling assignment. These are just pulled from your homework. We're asked to place the following steps of the scientific method. Pause the video now and have a conversation with a buddy nearby or in your own head if you're at home. Take a read through these, and I want you to list them in the proper order. What's the first step of the scientific method? All the way through to the last step. Pause, answer the question, and hit play again when ready to check your work. Well, here you go. How did you do? We know it begins with an observation, followed by a hypothesis to explain that observation. That hypothesis gets tested and revised and retested as needed. But then once it's confirmed, that hypothesis is not necessarily called a theory just yet, but it needs multiple confirmation by multiple people. That hypothesis may get accepted as a theory to the scientific community. Excellent work, friends. Here's 2 more vocabulary terms from this first section, the term independent and dependent variable. I'd like us to remember these definitions as well. An independent variable is a variable that is changed in an experiment. It tests the effects of the dependent variable. That's the other vocabulary word. It's the one being tested and measured. We change something in our experiment and see how it affects the variable. Now let's give an example to clarify. And I pulled one from your homework assignment. It reads that Julia wants to determine if temperature affects the growth of E. coli. After preparing 5 Petri dishes with equal amounts of nutrient agar, Julia transfers a drop of the E. coli broth into each of the dishes. As shown in the table below, she places each dish at a certain temperature. She measures and records the growth of the bacteria in each plate every day for 2 weeks. What is the independent variable in this example? What's being changed? Between the 5 dishes, we can clearly see the temperature is being changed. Now, what was she measuring based on changing the temperature? She was measuring the growth of the E. coli. So the actual, you can just see that here, she was measuring the growth of the bacteria in each plate, so that would be called the dependent variable. In our second section of Chapter 1, we begin to classify matter based on phase and composition. We distinguish between physical and chemical properties, physical and chemical changes. We should also know the 2 words intensive and extensive properties. We'll begin a discussion of density, which is the topic of your very first lab when you reach your lab session. We know that chemistry is the study of matter, and matter we define as anything that occupies space and has mass. Matter is anything that has density. We define density as a ratio of mass per unit volume. Matter can be classified in 2 ways. It can be classified by the phase, is it a solid, a liquid, or a gas? And it can be classified by its composition. Is it pure, element or a compound? Or is it a mixture, which are two or more items, two or more ingredients just blended together, but each retain its own identity? Let's explore each of those one at a time. Here's a slide that we'll look at and just kind of bring to mind some things I'm sure you already know in terms of properties of the phases of matter, of solid, of a liquid, and of a gas. What do you notice about the random or very ordered structure of the molecules? And think about the molecular level of solids, liquids, and gases. We know that gases take the shape of whatever container they're in, no fixed volume. It actually conforms to the volume of whatever its container might be. And gases is the only phase of matter that's easily compressed, which means I can take this size of a gas container and make it much smaller and still have the number of gas molecules fill that space, compressible. Liquids are not compressible. The molecules are too close to one another. Solids certainly are not compressible. They're very rigid structures. But the gas molecules are mostly empty space inside their container and therefore can be compressed or expanded. So at the molecular level, we see gases, they're very far apart and moving at very high speeds, randomly colliding to create a pressure inside of the system. The second phase of matter we call the liquid, with a distinct volume but no specific shape. So I can pour a liquid from one container to another and it will change shape depending on what the container might look like, but the amount of liquid is constant. And so you can see the liquid molecules kind of flow past each other. They roll by one another. Gases flow. Liquids flow, which mean the molecules can move past one another. Solids, of course, do not flow. They're in rigid, fixed positions. That third phase of matter, called a solid, both definite shape and a definite volume, very fixed positions. The molecules do wiggle and waggle slightly by one another. When we say they're wiggling slightly in their otherwise fixed positions, they do have a slight kinetic energy, but they cannot roll past one another. And so those chemical compositions of solid, liquid, and gas, there is a fourth state of matter known as plasma, but we will not be studying that in an ordinary chemical change. Now take a look at these visuals and see if we can decide which one would represent solid, liquid, gas, and plasma. And I'll just let you know the plasma is a charged particle area. So I'll go ahead and fill that in. And we recognize that solids have very fixed, rigid positions and an orderly arrangement. Liquids have a fixed volume, but they do have the ability to roll past each other. And we know that gases in their molecular arrangement are very spaced apart, freedom to move completely without bothering the other. The second way we classify matter is based on its chemical composition. Is it an element, a compound, or a mixture? We did that. Let's discuss each of these terms as we take a look at this flow chart. If you're in class, we talked about this with our neighbor, and if you're at home, we'll process together. The classification of matter is what I call this, the classification of matter pyramid. We have to be able to read this and determine, based on the chemical composition of some matter, how we would classify it into one of these four categories. So let's take a piece of matter, just something we're looking at. Does it have a constant composition? Does it have constant properties and composition? So when I look at it, am I looking at just one ingredient? If I am, it's said to be a pure substance. If it has more than one ingredient, and really when I say that, the correct vocabulary word is the term phase. One ingredient or one phase. More than one, two or more things mixed together create a mixture. Each retains its own identity. They're just blended together. So a nice word here might be the word blended together. If it's pure, one ingredient, it can be an element or a compound. An element, we know, is the basic building block of matter. Elements are built of atoms. Compounds are two or more atoms chemically bonded together, making a formula. Compound, and these are in our next slides, but we'll go ahead and jot them here, two or more elements chemically bonded together. An atom has a chemical symbol. We find them on the periodic table. A compound has a chemical formula that tells us the kinds and how many of the atoms in its arrangement. Come back over here and we're back to hetero or homogeneous. If the solution, which is another name for homogeneous mixture, is a solution, if it looks the same throughout, it's homogeneous. And if we see two or more phases blended, each of those looks different, and I can pick out the different particles, it's called heterogeneous. Hetero means different, homo means the same, describing how we see the mixture. Elements and compounds are pure matter. Elements cannot be broken down into simpler substances. It's only one kind of atom, and they're given symbols, which are one or two letters that abbreviate their names, and they must be found on the periodic table to be an element. Whereas compounds are also pure matter, but they're two or more electrically bonded together, either ionic or a covalent bond. Two or more kinds of atoms, and they're represented by formulas. So if I see a formula, two H's and an O, I now know that there's two different elements, hydrogen and oxygen, and all three of these atoms are bonded together to make a single substance called water. This is a substance called sucrose, which is table sugar, for example, and this is a substance here called sodium chloride, which is ordinary table salt. Those are called chemical formulas. They give us the kind of atom by the symbol and the number of atoms by the subscript. Keep in mind that a compound is chemically different than the elements that make them up. Water, for example, has different chemical and physical properties than the element oxygen and the element hydrogen. And in order to change a compound into its elements, it must undergo a chemical change. We have to break bonds. We can't just physically separate the elements or it'd be a mixture. We have to break bonds and let go of the elements that were once held together in that bond. And mixtures of variable composition, two or more things blended together, each retaining its own identity. And if those mixtures look the same, we call them homogeneous. Examples would include like a sports drink. It consists of water, sugar, coloring, flavoring, and electrolytes mixed uniformly throughout. Because it has a variable composition, we call it a mixture. A heterogeneous mixture is one that has variable composition, and I can see the different components by looking at it, such as Italian dressing. I can see a layer of vinegar, a layer of oil, herbs, things that settle apart over time. Which one of these looks like an element, compound, homogeneous, or heterogeneous mixture? Well, here I can see one type of atom in a fixed rigid position. It's only one shaded blue atom I'm going to put this one in the element. Here I can see that I have just one type of ingredient. These are all the same, so I know it's pure, but I see two different atoms bonded together to the central atom here. So I have a blue atom and two that are yellow shaded, but all bonded together. That's a compound. Notice here I have two very different ingredients that are not bonded together, but they're residing in the same container. Two distinct different layers is hetero. And here, these look more uniformly mixed together to create a homogeneous solution. Pause the video and process this and come back when you want to check your work. We're asked to just classify and see how many of each apply. We have nitrogen, oxygen, N2O, and air. N2, nitrogen. Nitrogen is an element. It has one kind of atom. N connected to an N is still one atom. It's the elemental form of the element called nitrogen. It is a pure substance. Elements or compounds are pure. Now, here's the elemental form of oxygen. So it must also be an element and pure. Here's three different atoms bonded together. Two of them are N's and the other is an O. All chemically bound together make it a compound. It's still just one ingredient, so we'll call it pure. Now, air is a blend of different gases together. We have nitrogen, oxygen, carbon dioxide, lots of different trace gases. And since it's composed of gases, and we know gases can diffuse evenly to fill the space evenly, we know that it's a homogeneous solution. It's a uniform blend of many different gases, making it homogeneous. Are you getting comfortable with the vocabulary terms? Let's try this example. Let me just read it through to you and see what you think. White gold, which is used in jewelry, contains two elements. It's got gold, and the other element is palladium. We take two different samples of the white gold, and they differ in the relative amounts of gold and palladium they contain. They're uniform in composition. They have a relative amount of gold. Now look, they have different samples with different amounts of gold and palladium. So for instance, I can buy a 10-karat gold ring, a 14-karat gold ring, an 18-karat gold ring, or a 24-karat gold ring. And what is different about them is the amount of gold they place into that mixture. So because it has a variable composition, it is a homogeneous mixture. I can create different degrees or different amounts of those two elements together, and yet they look the same throughout. I can't tell necessarily by looking if I have 10 karat, 14 karat, but I can tell really by how soft it is. Let's try another. Aspirin is composed of 60% carbon, 4.5% by mass hydrogen, 35.5% mass oxygen, regardless of where it comes from. Do you notice that those percentages are giving us what we call a definite composition? Since it has a definite composition, regardless of its source, has more than one type of atom bonded together, we're describing a compound between carbon, hydrogen, and oxygen. So in the previous example, because it was a variable composition, we knew it was a mixture. Here, because it's a definite composition, no matter where I find it, this is the percent by mass of each element, we know it's a compound. Let's try one more. If we have a blue solid and we heat it in the absence of air, two other substances are formed, a colorless gas and a white solid. What do we have? Element compound, homo or hetero. We're starting with a substance that's a blue solid, and we decompose that by heating it. We're taking a compound and breaking it down into simpler pieces. I know it's a chemical change because I'm making something new. If I start with a blue solid and after heating it, I'm seeing a gas and now a white solid, do you see how that's completely different than what I started with? This would be evidence of a chemical change. Now remember, mixtures, you just physically separate them, but they still retain the identity. With a compound, we have a chemical change to separate it into simpler things. So therefore, I know we're describing a compound because of the clue of that chemical change that took place. Excellent work, gang. This is section 3, and I'm going to pause the video just to give you time to rest. You can come back and pick up the lessons in section 3 when ready.